Okay, so because I'm bored, I'm going to take you through solving a problem. I'm just going to pull some random problem out of a textbook that I have from college and see if I can solve it. Okay, so we're in the darkened confines of my bedroom, and here's my bookshelf. Just going to pick a book from a subject that I don't feel too confident about and see what kind of problems it has to offer. Sure, let's pull a problem out of operating systems. Remember, this was a particularly sticky subject in college. So here's the book. Okay, here we go. Found this thing on Google. 7. So we're pulling a problem out of chapter 7. Let's go find out what chapter 7 is. Memory management. What a fun subject. So the first thing I like to do when I'm presented with a problem in this format, like in a college textbook, is write down the problem and do that freehand. Just copy the problem down onto a piece of notebook paper, and as I do that, try to absorb the information that I'm writing down. So after I've written things down very painstakingly and slowly and repeated all the words of the problem, just to keep track of which one we're doing, I'll make sure to label it with this chapter and section number. Okay. So without even looking at the book, I'm just going to try and figure out what I can about the question. Okay, so to implement the various placement algorithms. So just if we take this chunk on its own, it says various placement algorithms. Various means that there are one or more, probably, well, usually that means more than one. There's more than one algorithm for placement, basically is how I'm reading that. Now, placement of what? Well, we'll find out. Discussed for dynamic partitioning. So partitioning, I know that's how you, in this context, in the context of operating systems and in the context of memory management, partitioning refers to how do you divide main memory up into chunks to allocate to processes and programs, because they need memory in order to store the data, the necessary data, in order for them to function properly. Okay, so there's a reference to a section here, so if we need to find out what exactly dynamic partitioning is, we can refer to this section. A list of the free blocks of memory must be kept. This is just really a statement of fact. If you want to allocate memory to a program, you're going to need free memory to allocate to a program. So the operating system is going to have to decide which chunk of memory to give to a new process that's spun up. Okay, for each of the 3 methods discussed, okay, so here we get some specific algorithms for selecting from a list of free blocks of computer memory. What is the average length of the search? So now they're asking us, basically we have these 3 algorithms that we can use to select from a list of free blocks of memory. And we want to know what's the average time or length or computational work it's going to take for each of these algorithms to find a free block to allocate to a program. So a good place to start, there's a reference to section 7.2 here where some of these concepts are discussed. So we're going to flip to 7.2. And if we look here, there's a section called placement algorithm. That sounds promising. And then as we can see here, highlighted in bold are our 3 algorithms for choosing from a list of free blocks of memory. So I'm going to start reading from here because this is within the first couple words I can see of this paragraph. It says 3 placement algorithms. And if we look at our question, what is it asking about? It's asking about 3 methods for selecting free memory, which is basically the same as saying 3 algorithms. Okay, so I'm going to read here out loud and slowly to myself. 3 placement algorithms that might be considered are best fit, first fit, and next fit. All, of course, are limited to choosing among free blocks of main memory that are equal to or larger than the process to be brought in. Okay, so I'm going to slow down and just think about that for a moment. So all these algorithms are constrained to choosing free blocks of main memory that are equal to or larger than the process being brought in. So if we imagine the process being brought in being, let's say, 20 megabytes. I don't know if that's a good way to measure free memory, but I'm just going to go with it. Well, the block size then is going to have to be 20 or greater than that, 20 megabytes or greater. So if we read further here, best fit chooses the block that is closest in size to the request. So if there's a program that's requesting 20 megabytes of data, we have a free block of memory that is also 20 megabytes, then we are going to allocate that block and say we have other blocks of memory. One being, 10 megabytes, another being 30. We're going to allocate the 20 megabyte block to that process. So that's what I understand from the best fit algorithm. First fit begins to scan memory from the beginning. So if we think about memory being a really just long sequence of addresses, we begin scanning from the beginning and we choose the first available block that is large enough. Okay, that sounds simple enough. Next fit begins to scan memory from the location of the last placement. So here we're remembering where we last allocated memory and chooses the next available block that is large enough. So it's a bit like first fit, except for we don't begin the scan at the beginning of memory. We begin the scan at the last place that we allocated memory to a process. So luckily enough, I don't have to draw any pictures because the book provides some. So here we're operating in a dynamic memory scheme, which means that the allocated blocks of memory for a program and the free blocks are all variable in size and in their location. So it's not as if memory is divided into nice equal sections. Here it just depends on how much memory a program needs, and the selection algorithm picks where that program is going to be allocated. So if we look at this example, we have, and we follow the key here, we have an 8 megabytes of free memory, and if we just think of memory as a linear type thing, we have this block allocated. We have 12 megabytes of free. This one's allocated. It doesn't really say how much is allocated here, but we don't really need to know that information. We just care about how big are the free slots, because if a new program comes into main memory, we need to decide, okay, which of these free slots is that program going to live in. Okay, so we've got, so we've got all this free space here. So if we imagine this is what computer memory looks like at some point in time, and there's already been memory allocated to varying processes by the operating system. We now need to figure out, okay, using the best fit, first fit, and next fit algorithms, how long is it going to take for us to find that free block and select it in order to allocate it to that process? Capital N is the number of free blocks of main memory now. If that's the case, for each n, so for each free block of memory, so I'm just sort of reiterating what the best fit search is in my own words. For each free block of memory, find the difference between the memory needed, so the size of the program coming into the operating system, or coming into the computer's main memory as decided by the operating system. Find the difference between the memory needed and the memory available. And the memory available is just those free blocks that we were talking about. Okay, long story short, after a lot of dilly-dallying, the average length of time. Okay, so we're going to write this out, our answer here. So we're going to move to the paper. Okay. The average search length for best fit when selecting a free block of memory is n, where n is the number of free blocks in memory. So if you had, let's say you had 20 free blocks of memory, I guess that's worst case. No, it's n. Yeah, okay. If say you have 20 free blocks of memory, using the best fit algorithm, it's going to take you n searches for each of those free blocks. Yeah, it's going to take you n number of times in order, n number of computations in order to find the block that fits your program best. I'm sure somebody smarter than me can provide something a little more accurate. Okay, I'm introducing another variable now. Average search length is going to be m. Nope. What am I trying to say? For my initial analysis, best fit is the worst performing algorithm because you have to search the whole memory space to determine, right, you have to search the whole memory space, all free blocks, in order to determine which is going to be the best fit. So this is the worst one because n is going to be larger than n over 2 and also n minus m over 2. The next worst, in terms of number of searches, the next worst performing algorithm based upon my initial crappy analysis is going to be first fit. And that is because it takes approximately n over 2 searches in order to find the free block. The best performing is next fit. And that is because our search disregards memory that we've already allocated. So, you know, you can imagine a program running over time. It's going to, or you can imagine an operating system running over time is going to allocate blocks using this scheme. And at some point, just to confirm, begins to scan memory from the location of the last place. Okay. So we're going to begin our search for new memory for this program from the last place we allocated onwards. So that's going to reduce this search space that we need to traverse over looking for free blocks. And that search space is approximately the total number of blocks minus the number of allocated blocks. And within that search space, it's going to take us approximately half that number of blocks in order to find something that's going to fit our program. So this is the best performing from my initial analysis. So thanks for joining me in this exciting adventure exploring the process of problem solving, where I didn't really explain much about my process, but I gave you a taste of how I operate without doing much explanation of how I operate. There's a lot to learn. Just the best way to get better at it is to do it constantly and to practice constantly. Just find problems out of textbooks. Start trying to do them. Understand all the terminology used in the problems, and if you don't, make sure you read the sections, the relevant sections that are going to make you understand or help you understand what the problem is asking. Thanks for hanging in there. Keep hammering.